Hi everyone! Here we are going to continue solving for the eigenvalues, eigenvectors, and the corresponding eigenspaces of this given 3x3 matrix A. We are going to use this characteristic equation that is already provided on a separate video on the same matrix, since this characteristic equation will allow us to solve for the eigenvalues, the corresponding eigenvectors, and an eigenspace. To do this, we are going to because the three binomial expressions here, their product is 0, it would mean that what do you call this one? We can only say that this is true if all or one or two of these binomial expressions is equal to 0. So minus 3 equal to 0, lambda plus 3 is also equal to 0. You could see here our first lambda is negative 3, our second lambda is 3, and our third lambda is actually negative 3 as well. Notice that we have the same eigenvalue here. These are now the considered eigenvalues. So we have negative 3 multiplicity of 2. Okay? This would mean that we are only going to use negative 3 once. And since we have multiplicity of 2, it should be correct that there would be 2 eigenvectors for negative 3. Okay, so anyway, we're going to try it later and see what are the eigenvectors for negative 3, because there should be 2 as well here. So the next thing here is if we're going to return to this expression here, you have lambda I minus A, where our I is the identity matrix of a 3x3 matrix 1, 0, 0, 0, 1, 0, 0, 0, and then 1. So we have this form here. You have lambda times your I, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, minus your matrix A, 1, 2, negative 2, negative 2, 5, negative 2, negative 6, 6, and then negative 3. So you have lambda 0, 0, 0, lambda 0, 0, 0, and then lambda minus 1, 2, negative 2, negative 2, 5, negative 2, negative 6, 6, and then negative 3. So the final form, okay, for our expression, this one here, is you have lambda minus 1, 0 minus 2 is negative 2. You will have here 0 minus negative 2 is positive 2. Then 0 minus negative 2 is also positive 2. Lambda minus 5. 0 minus negative 2 is positive 2. We have positive 6, negative 6, and lambda plus 3. Okay? That's lambda minus negative 3. This matrix now will then be paired in this process. Okay? This is the expression here. Times a certain vector in R3, which comprises of x sub 1, x sub 2, and x sub 3 entries. Equate it to the 0 vector of R3, 0, 0, 0. Then we are going to solve for the correct values for x sub 1, x sub 2, and x sub 3, depending on the result of this expression when we substitute lambda as this first eigenvalue. Okay, so let's do that. Our first eigenvalue is negative 3. So negative 3 minus 1 is negative 4, negative 2, and 2. You have 2. Negative 3 minus 5 is negative 8. You'll have here positive 2 as well. This is 6, negative 6, and then you have negative 3 minus plus 3 is 0. This is to be multiplied with x sub 1, x sub 2, and x sub 3. Equate it to 0, 0, and 0. Here, the challenge is to come up with the row echelon form of this first, so that we could later on look for a strategy where we could connect the values of x sub 1, x sub 2, and x sub 3 to the possibility of having a arbitrary constant or some other variables. So to do that, hopefully the space are enough here. Let me multiply negative 1/4 to all the entries of R1 for us to have a new R1 here. This would mean you have negative 4 is equal to 1. Negative 2 will become positive 1/2. Positive 2 will become negative 1/2. This is still 2. negative 8, 2, 6, negative 6, and 0. Next, we'll make this 0 here. Okay, so multiply negative 2 to row 1 plus row 2 to have new row 2. Multiply negative 6 to row 1 plus row 3 to get a new row 3. Alright, so we have 1 and then 1 half, negative 1 half still. So negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 1 half is actually negative 1 plus negative 8, so negative 9. Negative 2 times negative 1 half is positive 1 plus 2, you have positive 3. The next row, negative 6 times 1 is negative 6 plus 6, 0. Negative 6 times 1 half is negative 3 plus negative 6 is negative 9. Then negative 6 again times negative 1 half is actually positive 3 plus 0. I have here 3. Notice that we have rows of the same entries. In our previous analysis before, we will have here a row of zeros. Let's try to move further. Let's try to multiply negative 1/9 to row 2 plus we'll have it first to make this as leading 1. So we'll have row 2. So we have here 1, 1 half, negative 1 half, 0. This would now become 1. This would be negative 1/3. We have 0, negative 9, and 3 here. So to make this 0, what you need to do is to multiply 9 to row 2 plus row 3 to have a new row 3. 1, 1 half, negative 1 half, 0, 1, negative 1/3, and you will have here 0. 9 times 1 is 9, minus negative 9 is 0. Okay, next, 9 times negative 1/3 is negative 3 plus 3 is 0. See, since we have rows of the same entries, we'll have here row of zeros. Now that it is already in a row echelon form, let's return to the form earlier, because we could see here that x sub 3 doesn't have any exact value. So we are going to let here x sub 3 be an arbitrary variable t. Okay, so if that would be the case, using the second row, you will have here x sub 2 and then minus 1/3 of t equals to 0. Or let me construct it correctly first. 1/3 of x sub 3 equal to 0. So x sub 2 minus 1/3 of our x sub 3, which is t, equal to 0. X sub t is 1/3 of t. Okay, so that's for our what do you call this one, x sub 2. Then for this last here, x sub 1 plus 1 half x sub 2 minus 1 half x sub 3 is 0. So x sub 1 plus 1 half of x sub 2, which is 1/3 of t, okay, minus 1 half t is equal to 0. So x sub 1 plus 1/6 of t minus 1 half t equals 0. This is actually 3/6. Okay, 3/6. Again, 1 half. Yeah, that's correct. 1 half times 1/3 is 1/6, right? So this is 3/6. So you have x sub 1, and you will have here 1/6 minus 3/6 is minus 2/6 or minus 1/3. T equals to 0. So x sub 1 is equal to 1/3 of t. Here, we consider there's only one vector here. This is very clear. Our eigenvector for eigenvalue, which is negative 3, is equal to, you have this, our first x sub 1 is 1/3 of t. Our x sub 2 is also 1/3 of t. And our x sub 3 earlier represented by t. Factoring t, you'll have 1/3, 1/3, and then 1. So we only have one eigenvector, even if our x sub lambda sub 1, our first eigenvector, is with multiplicity of 2. Probably this could give us 2 vectors later. So again, let's just try to work on it. In short, our eigenspace here is set of t times 1/3, 1/3, and 1, such that t is an element of R but not an element of a set containing 0. Eigenspace, eigenvector for this eigenvalue. So we only have one eigenvector here, even if our eigenvalue is with multiplicity of 2. Let us see, with our eigenvalue of 2, which is positive 3, if we could have 2 eigenvectors here. So using the same concept here, so 3 minus 1 is 2, negative 2, 2. You have 2, 3 minus 5 is negative 2, and another 2. Okay, you're seeing this already. Just like earlier, we are expecting rows of 0 here. And you have here 6, negative 6, and then 3 plus 3 is 6 as well. Aside from this, we have rows of similar entries, and the third row is also a multiple of either of those 2 rows. So we're expecting 2 rows of 0 entries, right? Per our previous analysis. But then again, I'm going to show you here the process so you could really see how it's done. Let's simply divide this region here. Alright. So for this row echelon form, okay, by analysis, again, we are expecting 2 rows of zeros. But let's show if there are really 2 rows of zeros after this process. So we have 1/2 of row 1 to make this a leading one. Okay. So you will have here 1/2 of 2 is 1, negative 1, and 1. So you have 2, negative 2, 2, 6, negative 6, and 6. See what happens here. Multiply negative 2 to row 1 plus row 2 to have a new row 2. Multiply negative 6 to row 1 plus row 3 to have a new row 3. Notice what happens. 1, negative 1, and 1. Negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times negative 1 is positive 2 plus 2, 0. This is also 0. So we have 1 row of zeros. Another, because we are expecting to have 2, because again, we have duplicates and multiples. So negative 6 times 1 is negative 6 plus 6, 0. Negative 6 times 1 is positive 6 plus 6, 0. Here, 0 as well. See? We have 2 rows of zeros as indicated by our previous analysis of having duplicate rows and 1 row which is a multiple of the other. If we're going to multiply this with x sub 1, x sub 2, and x sub 3 and equate this to 0, 0, 0, here's the thing. See what will happen. X sub 1 minus x sub 2 plus x sub 3 is equal to 0. We don't have any other equation here. In short, we will apply or implement here 2 arbitrary constants. For x sub 3, let's use s because we already used t earlier. And x sub 2, let's use w in this case. This would mean we have expected to have 2 arbitrary constants here. And with this, we can already imagine that there are 2 vectors. And this is how it looks like. X sub 1 now is minus w plus s equal to 0. So x sub 1 is equal to w plus s. Okay? So with all of this, our eigenvector here for our eigenvalue, which is positive 3, is in this form. W plus s. W and then s. What happens here is, of course, you could rewrite this as w plus s, the w plus 0, okay? And you have 0 plus s. So that you can break this into 2 vectors, w, w and 0, plus s, 0, and then s. See, we have 2 vectors here. As we take the first factor, take out w, you will have here 1, 1, 0. And as you take out s, you have 1, 0, and 1. So we have only one eigenvalue, you have two. This is part of your null space now. Okay? So if you're going to come up with the eigenspace for this, you're going to express it like this. Okay? Set of W110 plus S101 such that W S element of R but an element of set containing 0. Eigenspace, two eigenvectors, and you have here your eigenvalue. So this is the method of solving this, even if you will have similar eigenvalues here. So earlier we mentioned that it's possibility that since we have a multiplicity of -3 here, so this would create as two vectors. But in other way, as we shown here, there's only, even if there are when we say -3 as eigenvalue is as multiplicity of 2, we only have one vector here, eigenvector. Okay, but that other eigenvalue, only multiplicity of 1, it resulted to two different eigenvectors. Okay, thank you very much for watching.